Okay, so we talked about what empirical formulas are, how they come from experimental data. How do we do that? Well, there's a couple of ways. A common way is to either measure the masses of elements that combine to form a compound, or to take a known amount of compound and decompose it and measure what's given off. So that would give us masses of elements. We can also calculate an empirical formula if we have the mass composition of the compound. And a reminder that the empirical formula gives us ratios of atoms or moles of atoms, and it doesn't give us ratios of masses. So here are the steps for finding an empirical formula. We start with the masses of each element. If they give you a percent, you can convert that into a mass by just saying, well, let's assume we have 100 grams. Then the percent is the same as the mass. So you've got the mass of each element. You convert masses into moles, and then we look at the ratio of the moles. We do that by taking the smallest number of moles and divide everything by the smallest. And then hopefully we'll get nice whole numbers, but it doesn't always work out that way. So this is my guideline for when can I round it to a whole number. If it's within 0.2 of a whole number. So what does that mean? Well, if I had 1.93, I can round that to 2. If I had 4.19, I could round that down to 4. Because the difference between what I'm rounding and the whole number is 0.19. It's 0.2 or less. The difference here is 0.07. If I have something like 6.23, I can't round that. Okay, I have to do something else with that. This is what we do. If the subscripts are not whole numbers, then we're going to multiply all the subscripts by the same number to keep the ratio intact, but to get whole numbers. So fractions have decimal equivalents, right? So 0.5 is the same as 1/2. 0.33 is a third. 0.25 is a fourth. If it ends in 0.25 or close to it and I multiply by 4, I'm going to get a whole number. So if that makes sense to you, you can just pick the correct number and be done with it. If you're like, what are you talking about? There's a trial and error method that also works really well. Try multiplying by 2. Do you get whole numbers? Great. If not, start over with your original moles and multiply by 3. Multiply by 4. You usually don't have to go any farther than that. So we'll do an example that has that problem. But first we'll do a straightforward one. So a sample of compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. So they gave us the mass of each element. We're going to convert to moles. Then we're going to do a ratio, and hopefully we'll get whole numbers. So the first one they gave me is carbon. 165 grams of carbon. I need to convert this to moles. Moles of carbon, grams. 1 mole of carbon is 12.01 grams. So this gives me 13.7385521. Do not round too much here. So I should have 3 significant figures. It's best to keep a couple extras. You can keep all of them if you want to. But if you rounded this, say, to 14, you're going to mess up your formula. So I'm going to keep 2 extra digits because that's what I like to do. So there's moles of carbon, 27.8 grams of hydrogen, 1 mole of hydrogen, grams of hydrogen, 1.008. 27.579 moles of hydrogen. And 220.2 grams of oxygen. And 13.7625 moles of oxygen. The hardest thing about these is remembering what I'm supposed to do. Take the masses of the elements, convert to moles of the elements. So we could use these as subscripts in the formula, but they're not whole numbers. And we can't just round them to whole numbers. We're going to look at the ratio. And so we're going to pick the smallest of these, which is the 13.738, and we're going to divide everything by that. So obviously for the smallest that gets divided by itself, we're going to get 1. For the hydrogen, 27.579 divided by 13.738 equals 2.007. And the one on the bottom there, gives me 1.0017. This one's always a whole number. Is this close enough that I can round it? Yeah. Can I round this one? Yeah. So this becomes 2, and this becomes 1, and those are the subscripts in my empirical formula. They gave me the elements in order: carbon, hydrogen, oxygen. Just keep them in the same order. Carbon, 1, but I don't write a 1. Hydrogen, 2. Oxygen, 1, but I don't write 1. So there's my empirical formula. Any questions? Let's do another one. Here's ibuprofen. We had the formula earlier, but let's look at calculating it. So here we're given mass percent composition and asked for the empirical formula. So we say, well, let's assume I have 100 grams of ibuprofen, then 75.69 grams are carbon. So I just take the percent sign and make it into a gram. So 75.69 grams of carbon. Doing the same thing here. I'm just converting to moles. This time I'm going to just see what happens if I keep the minimum number of significant figures and live life on the edge today. 8.80 grams of hydrogen, converting to moles. .73. So this is moles of carbon, moles of hydrogen. 15.51 grams of oxygen. So I converted my masses to moles of elements. Bless you. And now I need whole numbers. So I'm going to divide by the smallest, 0.9694. So that's going to give me 1. I divide by the smallest because then all the others are going to be bigger than 1. Right? They're going to be 1 or larger. I don't want any more partial, fractional numbers. So 8.73 divided by 0.9694 gives me 9.006. Well, about 9.01. This one, $66.302. Start over. 6.302 divided by 0.9694. This one equals 6.501. Well, that 9.01 is nice, but 6.5, can I round that up to 7? No, it's halfway between 6 and 7. So I need to multiply it by a small whole number to get a whole number. So 0.5 is the equivalent of 1/2. This is 6.5. If I multiply by 2, and actually do it on your calculator. I got that 6.501 times 2, 13.002. Can I round that? Yeah. I need to keep the ratios intact, so I have to do the same thing to both of the other ones. So this is 18.02, and this one is 2. Yeah. Yeah, if it was 6.9, yeah, you could round it to 7. Yeah. The reason that we had to multiply here is that the ratio is 13 to 18 to 2. That can't be simplified any further. We've got this odd number in here. So this can be rounded to 18. This is rounded to 13. So carbon, 13, hydrogen, 18, oxygen, 2. Empirical formula for ibuprofen. Yes. I don't know what happened to the 8. There it is. Thank you. Mm-hmm.
So is it always going to give it to you in the smallest number? Or like if you did the formula and you ended up getting like 16 to 2 for an answer?
So when you get the moles and divide by the smallest, that will always give you the lowest possible ratio because the smallest number will be 1. Sometimes that's too small because the smallest number in the formula is actually 2 or 3, and that's why we end up having to multiply. But you shouldn't ever end up with something that gets too big that you have to simplify. So, any other questions? That gives us the empirical formula. To calculate the molecular formula, we need more information. We need the molar mass. So the molecular formula is the empirical formula times some number. Because when you take the molecular formula and you make it simpler, what you're doing is you're dividing out a common factor. So if we take the empirical formula, we have to multiply by that factor to get back to the molecular formula. But how do we know what that number is? We take the molar mass of the actual compound. That has to be given to us. And we're going to divide it by the mass of the empirical formula. because we want to know how many times does the empirical formula fit into the molecular formula. That gives us n, and we multiply all the subscripts by n.
We can't figure out the molar mass. Oh, because we don't have a formula.
Yeah,
Never mind.
yeah, it's circular, right? We can't figure out the molar mass of the compound because we don't know the molecular formula, and so if we don't, yeah, go around and around. So how do they find the molar mass? Another way, you can do experiments that'll get you the molar mass, or you can use a mass spectrometer to get the molar mass. There has to be some other way. So a compound has an empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? Well, what's the mass of this empirical formula? CH. It'd be 12.01 plus 1.008, so 13.018 grams per mole. Is that the same as the actual molar mass? No, it's too small. How many times does this go into that? Well, we don't need to guess, we can just divide. 78.11 grams per mole divided by the mass of the part, bless you, 6.00015, blah, blah, blah. This should always give you a number that can be rounded to a whole number. It should always come out very nice. If it doesn't, you're doing something wrong. You're calculating your empirical formula or its mass incorrectly, or you're doing the math wrong. There's no multiplying by factors here. So this is 6. So there are 6 of the CHs in the whole molecule. So you can think of it as CH multiplied by 6, if that helps you. But the formula is C6H6. If I took this and asked you, what's the empirical formula? You'd find the lowest ratio, 6 to 6 is 1 to 1, and you'd give me CH. Any questions? Yes?
So, like, using different periodic tables will give you slightly different masses, right? But it's going to be so close that we're still going to get nice numbers.
Right.
Okay.
So if you use a rounded 4 significant figure molar mass, or if you use all the digits on the periodic table, your answer here might vary in the last digit, but it shouldn't vary anywhere else, and so you're still going to come up with a nice whole number. When you round things too much, like when you round the molar mass of chlorine 35.45 to 35, then you start messing things up. So that's why I don't want you to go to less than 4 sig figs. Any other questions?
The CH in the parentheses with the 6, that's not as correct as the C6H6?
Right. This is sort of a toddler way of writing it down. I know what you mean, but that's not how you would write the formula. Yeah. Anybody else?